Good afternoon, everyone. So, I welcome you all once again for the problem solving session for the NPTEL course Computational Fluid Dynamics. The course code is NOC 25CH18, and we are almost towards the end of the session. We are in week 12, and this session has been happening every Saturday from 3 p.m. to 5 p.m. The course instructor is Professor Sreenivas Jayanti from the Department of Chemical Engineering, IIT Madras, and the TA is myself, Ankara Kartiga. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So, moving forward, we will wait one more minute for others to join and we will start the session. Alright, um, we'll start now. So, as you all know, this is a 12 weeks course, and we have almost covered from the basics, and we are into 12th week. In the first week, we have seen about the introduction to the calculation of flow in a rectangular duct, wherein we saw the introduction about the finite difference approach. And second week, it is about calculation of fully developed flow in a triangular duct, wherein we saw about the flow through a triangular duct by means of finite volume approach. And in week 3, it is about derivations of equations governing fluid flow. When we talk about CFD, as you all know by now, that we mean that we are solving the system of equations using the computational resources that are available to us. So, what are the system of equations? If it is a fluid flow problem we are considering, then we solve for the continuity equation and momentum conservation equations, because ultimately we want to know what is the pressure and what is the velocity inside the system, and for that we need to know the equations of continuity and equation of momentum conservation, which we obtain from the basics in those things. So next week it was about equations for incompressible flow and boundary conditions. Also, when we solve for the system of equations, we apply a certain boundary conditions, and this boundary conditions, uh, for example, in fluid flow in a pipe, we give the inlet velocity, or if you are heating a rod, we give the source information at one end. So something or the other information which we know at our hand, we give in the form of boundary conditions, that is we give the values at the boundaries. And for incompressible flow, as we all know, there is no density variation, so it becomes constant. So in the continuity equation, it becomes common, we take it out and becomes 0. And week 5, it is about basic concepts of CFD using finite difference approximations, wherein we use the Taylor series approximations and those things. And week 6, it is about basic concepts of CFD, consistency, stability and convergence. And week 7, it is solution of Navier-Stokes equations for compressible flows. And week 8, it is about solution of Navier-Stokes equations for incompressible flows. So what we studied in week 6, it is about consistency, stability and convergence, because unless we know that we will get a converged solutions, we if we proceed without knowing there is assurance of converged solutions, we may end up with uh, solutions which are not converging, and they might be diverging. So these things we need to assure, that is consistency and stability. And when we talk about week 7 and 8, it is about solution of Navier-Stokes equations using various approaches. In the first week, it was about compressible flows, wherein we use approaches like McCormack scheme, beam warming scheme, etc. Because the flow was compressible flows, we were able to solve the equations as such. And when we talk about incompressible flows, the density was constant, it wasn't varying, so in the continuity equation it vanishes. So there were various approaches like artificial compressibility approach, wherein artificially one factor was introduced similar to the density in the equation, continuity equation, and the solutions were obtained. Or there are other methods like stream function vorticity approach and pressure velocity uh, approaches, pressure correction approaches. Those things were there, which we have seen in the week 8 problem. And in week 9, it is about solution of linear algebraic equations using basic methods. Basic methods like Gauss-Seidel method, Jacobi method, all those things we have seen in the week 9. And week 10, it is about solution of linear algebraic equations using advanced methods, wherein we have seen few schemes uh, which you might not use, but to get awareness on those, we have seen about solution of linear algebraic equations using advanced methods like alternating direction implicit, ADI scheme, and SOR, successive over relaxation. Those methods we have seen. And last week it is about basics of finite volume method including grid generation, wherein we saw mostly about structured mesh and unstructured mesh. And lastly, it is about turbulent flows and turbulence modeling, which we will be covering in today's class. So for the books and references, we have 5 books. First one is Ferziger and Perry, Computational Methods for Fluid Dynamics. And second one, it is Hirsch C 1988, Numerical Computation of Internal and External Flows. And third one, it is Patankar SV 1980, Numerical Heat Transfer and Fluid Flow, Hemisphere, Washington DC, USA. And fourth one, it is Westig HK and Malalsekara W 1995, an Introduction to Computational Fluid Dynamics, the Finite Volume Method. And last one, it is Anderson JD 1995, Computational Fluid Dynamics, the Basics with Applications. So I hope by now you all would have seen few of the books and would have read from those as well. So these need no new introduction to you people. And in today's class, we are in week 12 problem solving session. So in theory classes, I hope you would have attended and would have come to know about turbulence flows and turbulence modeling. So to give you an idea, today's problem solving session will be revolving around that only. And yeah, one more announcement to make. We will be having one more session tomorrow, where it will be from 6 p.m. to 8 p.m., where I will give some problems from all weeks, and we will discuss and we will get the solution. If there are any doubts from previous classes, we can discuss tomorrow, or it will be like a summary session to end up the session, because this is 12th week, we are almost over. So one more session to just cover all the problems, all the concepts, and that will be like quick revision for you people as well to appear in the exam. So that is the motto behind it. And yeah, we'll start now. So first question in week 12, it is about which of these is a characteristic feature of turbulent flows? Which of these is a characteristic feature of turbulent flows? First one, it is chaotic fluid motion. Second one, high diffusivity. Third one, high frequency fluctuations. So we are given 3 features and we are asked to find which one is are which are the features of a turbulent flows, and we are given chaotic fluid motion, high diffusivity, and high frequency fluctuations. Option A 1, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So we all know that the answer is option D, that is 1, 2 and 3. Okay, I'll just insert slide number, without it it is bit difficult for me. Slide number. Oh, just a minute, I am just fixing something. I'll come. So yeah, when we talk about characteristic feature of turbulent flows, we know that the turbulent flows experience chaotic fluid motion, they experience high diffusivity, and they experience high frequency fluctuations as well. So what is turbulent flows? Turbulent flows are nothing wherein the Reynolds number is so high that we no longer see the structured flow which we commonly see in laminar flows. So that becomes disrupted and we will be seeing a very random motion at high frequency. So this is the general characteristics of features of turbulent flows. So the answer is therefore option D, that is 1, 2 and 3 is the right answer. Alright, option D is the right answer. Turbulent flows are characterized by chaotic changes in pressure and flow velocity. So option D is the right answer. Now we are going to question 2. In question 2 it is given that the time interval for time averaging of flow governing equations should be such that the time interval for time averaging of flow governing equations should be such that dash. First one, it is as large as possible. Second one, it should be much larger than the time period of the largest eddy. Third one, it should be larger than the time period of the smallest eddy. And fourth one, it should be much smaller than the time period of the smallest eddy. So what is we are doing? We are just time averaging things. And what is our main focus? We should focus that one the time averaging is covering that event completely. So what should be the time interval? It should be should it be like larger than the time period of the largest eddy? As it should be larger than the time period of the largest eddy, because only then we will get to know the complete information regarding that largest eddy, regarding the largest eddy. So option A means that it is as large as possible, but it doesn't give any quantitative information on the time. we can't choose that. Second one, it should be much larger than the time period of the largest eddy. It is true. It should be, the time period should be larger than the time period of the largest eddy. Only then we can get to know the complete information about that eddy formation, and it will be useful for the time averaging. And C, it is given that it should be much larger than the time period of the smallest eddy. It is false, because if it is the smallest eddy, we will capture the information related to the smallest eddies. But what about the smaller, larger eddies and the largest eddy? We would not know. So this is false. Again, it should be smaller than the time period of the smallest eddy. If it is smaller than the time period of the smallest eddy, it would not even capture information regarding the smallest eddy. So option D is false. So answer is option B. That is, it should be much larger than the time period of the largest eddy. Option B is the right answer. So as we can all see, option B is the right answer. So the time interval for a time averaging turbulent flow governing equations should be much larger than the time period of the largest eddy. This ensures the statistical representation. The averaging period must capture enough turbulent fluctuations to eliminate randomness, leaving a stable mean flow. That is, we are using the averaging period, which is enough to capture the turbulent fluctuations, so that we are not focusing on any randomness. We are ruling out the possibility of randomness and having a stable mean flow. So eddy time scales, largest eddies dominate the flow's energy and have the longest time scales. Largest eddy have the longest time scales. So we need to know the, we need to cover that longest time scale. Smallest eddies dissipate energy and have much shorter time scales. If time interval is too small, that is smaller than the largest eddies period, fluctuations from large eddies persist in the mean flow, violating Reynolds average assumptions. Conversely, exceeding the smallest eddies period is automatically satisfied when the interval is large enough for the largest eddies. So I hope you are clear with this. If the time period is too small, right, the fluctuations from large eddies persist in the mean flow, and we will be violating the Reynolds averaging assumptions. But if on the other hand we are using the largest eddies, time period larger than the largest eddies, we are ensuring that smallest eddies period is also automatically satisfied, because here we have seen that largest eddies have the longest time scales, smallest eddies have these shorter time scales. So if we go with longer time scales, we will automatically cover the events happening with the smallest eddies also. So that is question 2. Now thus the correct criterion prioritizes the largest eddies time scale to ensure all turbulent motions are averaged out. So I hope it is clear that time interval for the time averaging turbulent flow should be much larger than the time period of the largest eddies. Why? Because largest eddies have the longest time scales and smallest eddies have the shorter time scales. If interval is too short, we will be not able to capture complete fluctuations arising from the largest eddies. Whereas if interval is long enough, we will be able to capture the fluctuations from the small eddies as well as from the large eddies. So we need to have that larger time scale than the largest eddy. So this is question 2, and I hope you are clear with the answer. Now time period, time interval for time averaging of flow governing equations should be such that it should be larger than the time period of the largest eddy. Now we will go to question 3. In question 3, what is asked? Mixing length varies with option 1, fluid viscosity, option 2, Reynolds number. Option 3, normal distance width from wall. So when we are talking about Prandtl's mixing length, we know that it is directly proportional to the normal distance from the wall. So 3 is the right answer. So given the options, option A 1, option B 2, option C 3, option D 2 and 3. So we know that only normal distance from wall is the right answer. So answer is option C. Option C is the right answer. Prandtl's mixing length is the distance a fluid particle travels before it gets mixed with the surrounding fluid particles. So it is the mean distance a fluid particle travels before it gets mixed with the surrounding fluid particles. So it is varying with the normal distance from the wall. Mixing length variation in turbulent flows is being dependent on the normal distance from the wall. According to Prandtl's original formulation, in the near wall turbulent flow, it is assumed that L is proportional to the normal distance y from the solid wall. That is, L is proportional to the normal distance y from the solid wall, where L is the mixing length and y is the distance, normal distance from the solid wall. So L is proportional to y, and that proportionality we are giving it as kappa. So L is the mixing length, kappa is the Kármán constant approximately 0.4, and y is the normal distance from the wall. So mixing length variation in turbulent flows is being dependent on the normal distance from the wall. That is actually coming from the Prandtl's original formulation, wherein it is stated that in the near wall turbulent flows, it is assumed that L is proportional to the normal distance y from the solid wall, and L is the mixing length and y is the solid normal distance from the solid wall. And for that proportionality, we are introducing the constant Kármán constant, which is approximately 0.4 in most cases. So regarding other two things, one was fluid viscosity. We know that mixing length was not proportional to the fluid viscosity. One more thing we had was Reynolds number. So regarding Reynolds number dependence, while turbulence characteristics generally depend on Reynolds number. So how we calculate the flow criteria, that is based on laminar flow or Reynolds number. We calculate, when we say flow is having low Reynolds number, we say it as laminar flow. Similarly, if flow is having high Reynolds number, we call it as turbulent flows. So it is turbulent flows is arising from the Reynolds number dependence. While in generally we can say that flow or the turbulent characteristics is depending on Reynolds number, there is no clear functional relationship, direct functional relationship between the mixing length and the Reynolds number. The mixing length formulation is primarily concerned with the spatial variation, that is how much it is away from the solid wall, concerned with the spatial variation rather than Reynolds number dependence. Mixing length is again a flow property rather than a fluid property. So mixing length model describes geometric and flow properties rather than varying directly with fluid properties like viscosity. So in the question it was given that mixing length variation is proportional to mixing length varies with dash, fluid viscosity, Reynolds number, distance from wall. So now we know that it is a flow property and not a fluid property. So it is not proportional to the, or it is not varying with the fluid viscosity. Second one, it is Reynolds number. While we calculate the turbulent characteristics based on Reynolds number, mixing length is not varying directly through any relationship. We are not able to observe anything from the literature. So it is not varying with the Reynolds number. And third one, but it is varying with the normal distance from the wall. So it is directly proportional, and we are introducing proportionality constant. That is one thing. So answer is option C. That is normal distance from wall is the right answer. So I hope you are clear enough. So yeah, now we will go to question 4. In question 4, what is asked is that we are solving the case of steady developing turbulent flow between two infinitely wide parallel plates using the K epsilon turbulence model. For this case, the number of differential equations that we need to solve is dash. So what is given? We are solving the case of steady developing turbulent flow between two infinitely wide parallel plates using the K epsilon turbulence model. And how many partial differential equations we need to solve. So in general case, if it is not a turbulent flow and we are, okay, let us just consider a flow through a circular pipe, cylindrical pipe whose cross sectional area is circular. So how many partial differential equations we solve in such cases? We have seen these in the earlier classes itself, and we know that we will be solving for one continuity equations and three momentum conservation equations in the pipe flow, x, y and z, or depending on coordinates whatever, r, theta, z, x, y, z. But we will be having to solve four partial differential equations. Now let us add one more thing. Instead of the circular pipe, now we are solving for flow between two infinitely wide parallel plates. So since it is infinitely wide parallel plates, what can we infer from that? We can infer it as a two-dimensional approach. So we will be having to solve two momentum conservation equations and one partial differential, one continuity equation. So we will have three equations. Now, instead of laminar flow or the regular flow which we observe in our cases, we are going one step ahead and we are having to solve for the turbulent flows. And what method we are using? We are using K epsilon turbulence model. So through K epsilon turbulence model, again what we will be able to see, we will be able to see that we have to solve for additional equations. One is K equation and one is epsilon equation, that is turbulent kinetic energy dissipation rates. Those equations, we kinetic energy and kinetic energy dissipation rate, two equations we need to solve. Clear? So already we had three equations. Now we are adding two more, that is one K and one epsilon equations. So finally we will be having five equations, five partial differential equations we need to solve. Looking at options, we will have option A 5, option B 4, option B 4, option C 3, option D 2. So the total number of equations is one continuity equation, two momentum conservation equation and two turbulence equation. So we have five equations on the whole. So answer is option A is the right answer. Option A, that is 5. So I hope you are clear now. So I need one thing actually. So animation. Little bit. So now we know that we need to solve for 5 partial differential equation. Alright. Okay. Now we have seen 4 similar problems to lay foundation for what we are going to see. So we are now having one case study. In this case study, we will be seeing one application wise problem, and later on you can apply similar concepts for the assignment submission and submit those assignments as well. If you want to solve any particular problem in tomorrow's class, let me know by the end of this session so I can arrange accordingly. Well, now this is our problem statement, and we are having a flow through a pipe. So here we are able to see that it is a flow through a rectangular duct, and fluid is flowing with inlet velocity V in, and okay, just ignore that. Vt velocity, and it is given by V in into 1 plus T V in into 1 plus T to the power of 1 by 2. So that is our inlet velocity. And now what we are going to see is we are having one statement, and consider this as figure 12.1, because in subsequent problems we will be denoting it as figure 12.1. So we are having unsteady turbulent developing flow of water whose density is 1000 kg per meter cube, and viscosity mu is 0.001 Newton second by meter square, through a rectangular duct of dimensions L into W into H, such that L is very much greater than H and W is equal to 1.5 times of H. Inlet velocity is uniform across the plane but varies with time as shown. So velocity is uniform across the plane, but it is varying with time, and it is given as V inlet into 1 plus T to the power of 1 by 2. Outlet can be considered as zero gauge pressure surface. So this is figure 12.1, wherein we are having a water flow through this rectangular duct, and this rectangular duct has length L, which is very much larger than its width, and height, this is H. So width is 1.5 times of height, and length is very much greater than height. So this is the cross section of the pipe, and the inlet velocity is uniform across the plane, that is inlet plane, but it is varying with respect to time. So it is given by Vt is equal to V in into 1 plus T to the power of 1 by 2. And what else? We are having water flow, and the flow is unsteady, turbulent and developing flow. It is not a steady state or developed flow. So it is an unsteady, turbulent and developing flow of water. Rho is 1000 kg per meter cube, and mu is 0.001 Newton second by meter square. And we are having the rectangular flow through the rectangular duct whose dimensions we have given, and in this inlet velocity and outlet is zero gauge pressure surface. So that is the problem statement. Now we will move to the problems. We have first question from this set, that is, if h is equal to 2 centimeter, that is height of the inlet is 2 centimeter, what is the value of V in for the flow to have a minimum Reynolds number of 50,000? If h is equal to 2 centimeter in figure 12.1, then the value of V in for the flow to have a minimum Reynolds number of 50,000 is dash. Option A 1 meter per second, option B 2.1 meter per second, option C greater than 2.5 meter per second, option D less than 0.25 meter per second. So we are given that height is 2 centimeter. If height is 2 centimeter, width is 1.5 times of height, so it is 3 centimeter. And we are asked to find the V in, that is V in when the Reynolds number is 50,000. So Reynolds number formula is given by rho V d by mu, and here V is unknown, rho is given, mu is given, and we need to calculate d. Because it is a rectangular duct, we need to calculate the hydraulic diameter, and everything else is given. So if we calculate, we will get the answer, and that answer is actually option B, 2.1 meter per second is the right answer. How we are now going to solve it here? So if h is equal to 2 centimeter, W is equal to 1.5 times of h, and it is 3 centimeter now. Options, Reynolds number is given as 50,000, and Reynolds number is given by rho V d by mu, and d is given by that is hydraulic diameter is given by 4 times the cross sectional area divided by 2 times the wetted perimeter, and therefore it is 4 into cross sectional area is W into H divided by 2 times of, okay, it is once again. It is not 2 here. Four into cross sectional area divided by wetted perimeter, and wetted perimeter is 2 times of W into W plus H, 2 times of A plus B. So what is the cross sectional area of rectangle? It is A into B, and similarly perimeter is 2 times of A plus B. So similarly 4 times of W into H, that is the area of the rectangular cross section, divided by 2 times of W plus H. So we are substituting the known values, that is W is 2, H is 3, divided by 2 into 2 plus 3. So 4 into 2, it is 8, 3 is 24, divided by 2 into 5, that is 10. So 24 by 10, it is giving us 2.4 centimeter. So it is 2.4 into 10 power minus 2 meter, that is the hydraulic diameter. Now we are substituting back in this. V in is equal to Re into mu divided by rho into d. Alright, we are just reframing this formula, and we are getting the velocity inlet as Re into mu divided by d into rho. So Reynolds number, we know it as 50,000. Mu is 0.001 divided by 2.4 into 10 power minus 2 into 1000. So 50,000 you can calculate if you want. We will calculate once just to okay, yeah, it is 2.0833. So roughly rounding off, we will get it as 2.1 meter per second. So that is how we are getting the value as 2.1 meter per second. I hope you are clear now. So I hope you are clear. Now, okay, and now we are going to question 6. In question 6, it is given that we wish to simulate the flow through the duct shown in figure 12.1, that is flow through the rectangular duct using the K epsilon turbulence model. Which of the following statements is or are correct about the Reynolds average Navier-Stokes equations? So what is given? We are just going to solve the flow through the duct, which is given in figure 12.1 using the K epsilon turbulence model, and the following statements are given with regards to that. We need to identify the correct statement. First one, it is given that we need to solve Rand's equation, that is Reynolds average Navier-Stokes equation. Second one, we need to solve unsteady Reynolds Rand's equation because the flow is turbulent. Third one, we can use the steady state form of the Rand's equation because the equations are time average. First thing, in the problem it is clearly mentioned that we are dealing with the unsteady developing flow systems. So we need to consider the unsteady state into our equation when we are doing that. So keeping in mind that thing, first statement given is that we need to solve Rand's equations. It is not stating anything beyond that fact that we need to solve Rand's equation. So we cannot go with that. Second one, it is given that we need to solve unsteady Rand's equation because the flow is turbulent. This is true because we are dealing with the turbulent flows. We are actually solving for the Reynolds average Navier-Stokes equations, and here it is given the unsteady system. So we are having to solve for the unsteady Rand's equations. So second one is true. Third one, we can use the steady state form of the Rand's equation because the equations are time averaged. This is false because we cannot go with the steady state form of the Rand's equation because even though the equations are time averaged, we are explicitly given that we are dealing with the unsteady system. So third one is false. So out of it, second one is true. And going with that, we are seeing it option A1, option B2, option C3, option D none of the above. So answer is, we know now that answer is option B2, not D2. So option B2 is the right answer, and we will, okay, as we have seen that we need to solve, okay, I haven't given, but yeah, we need to solve for the unsteady Navier-Stokes equation because the flow is turbulent. Okay. I hope it is clear. Now we will go for question 7. Now we are going to question 7. In question 7, we wish to simulate the flow through the duct shown in figure 12.1 using the K epsilon turbulence model. How many partial differential equations do we need to solve? So, the system we are dealing with is a rectangular duct flow through a rectangular duct whose dimensions are given. So, we will be having 3 dimensions in it. Uh, okay, options we will see first. Option A 4, option B 5, option C 6, option D 7. So we are using K epsilon turbulence model. So we will have additional 2 equations from the K epsilon turbulence model itself. Also we have 3 momentum conservation equations corresponding to the dimensions in the problem, and 1 continuity equations which we all know. So 1 continuity equation, 3 momentum conservation equation plus 2 uh, turbulence equations, that is 1 K equation and 1 epsilon equation, that is turbulent kinetic energy and turbulent kinetic energy dissipation rate. So we will be having on the whole 1 plus 3 plus 2, 6 equations we will have. The number of equations is equal to 1 continuity equation, 3 momentum conservation equation and 2 turbulence equations. So total it is 6. Answer is therefore option C, 6 is the right answer. Now we will go to question 8. In question 8, it is mentioned that which of the following statements is true about Reynolds average Navier-Stokes equation, RANS equation. First one, they can be used for time dependent turbulent flows. Option B, they cannot be used for slow transient flows. Option C, they can be used only for rapidly fluctuating turbulent flows. None of the above. So we are given 3 statements and asked to identify if any one of them are true or all of them are false. First one, they can be used for time dependent turbulent flows. This is a true statement. We will see the reason in the next slide actually. Similarly, the second and third statements, they cannot be used for slow transient flows is false. They can be used. And third one, they can be used only for rapidly fluctuating turbulent flows is also false, because we cannot restrict the use of RANS equations to only rapidly fluctuating turbulent flows. So B and C are false, whereas option A is true. Alright. So looking at options also, option A, they can be used for time dependent turbulent flows is the right answer. And we were just seeing the expansion to it. They can be used for time dependent turbulent flows. So these are the statements given in the question. So we are seeing why it is false. First one, they can be used for time dependent turbulent flows. So actually this is true statement. They can be used for time dependent turbulent flows. The RANS equation, while primarily developed for time average solutions to turbulent flows, can indeed be applied to time dependent transient flows through their unsteady variant known as URANS, that is unsteady RANS. It is relatively straightforward process to produce an unsteady variant of the RANS equation for turbulent flows while still solving for the mean flow velocity separately from the turbulent velocity fluctuations. So what is given? The Rand's equation was primarily developed for time average solution to turbulent flows. It can, although it was developed for time average solution to turbulent flows, it can be applied to time dependent flows, that is unsteady problems, through the variation known as unsteady variant of RANS. U-RANS, unsteady RANS, unsteady Reynolds average Navier-Stokes equations. So it is a straightforward process to produce an unsteady variant of the RANS equation for the transient flows while still solving for the mean flow velocity separately from the turbulent velocity fluctuations. So that is true. Second one, they cannot be used for slow transient flows. While this statement is actually false, because they can be used for slow transient flows. RANS or URANS models can definitely be used for slow transient flows. They can be used for only for rapidly fluctuating turbulent flows. Again, this is false because it is incorrectly restricting the RANs to only turbulent, rapidly fluctuating flows. RANs is specifically designed to average out rapid fluctuations rather than resolve them directly. The Reynolds averaging approach works by decomposing a turbulent flow into mean flow component and a fluctuation magnitude component. RANs can be applied to wide range of turbulent flows with different characteristics, not just those with rapid fluctuations. So what is stating in this problem statement is that RANs can only be used for rapidly fluctuating turbulent flows. It is incorrectly restricting the usage of RANs to this particular flows because RANs is designed for specifically designed to average out the rapid fluctuations rather than resolve them directly. We are not resolving any fluctuations arising from the flows, rather we are just averaging them. So that is the methodology behind RANs. It works how it works. It works by decomposing the turbulent flow into a mean flow component and fluctuating component. We have two components, one is mean flow and one is turbulent fluctuating flow. So this is how it works. It can be therefore applied to a wide range of problems with different characteristics. We need not restrict only to rapidly fluctuating problems. So this is again false. So of the given statements, the truer one is they can be used for time dependent turbulent flows, whereas the false cases are they cannot be used for slow transient flows, and similarly they can be used only for rapidly fluctuating turbulent flows is also false. So like I hope you are clear. The RANs or URANs, that is unsteady RANs, is designed for like averaging out the fluctuations. We are not resolving any of the fluctuations directly, rather we are averaging out the fluctuations, and it works by decomposing a turbulent flow into two components. One is mean flow component and next one is the fluctuation magnitude component. By doing this, we can apply it to a different range of turbulent flows with different characteristics, not just restricting to those with rapidly fluctuating turbulent flows. Similarly, the U-RANs, that is unsteady RANs, can be used for slow transient flows, which we have seen in the previous case also. That is, we are using a variant of the RANs model known as unsteady RANs. It is a straightforward process to produce an unsteady variant of the RANS equation for transient flows while we are solving for the mean flow velocity component separately from the turbulent flow fluctuations. So that is for this problem wherein we are able to observe that only first statement is true. Okay, all right. Okay, before moving to question 9, let it be here. or I'll keep question 9 here. Which of the following flows are likely to be turbulent? First one, flow in a circular pipe at a Reynolds number of 50,000, flow over a sphere at a Reynolds number of 50,000, flow over the plate at a Reynolds number of 50,000. So these are all the cases which are given. So let it be here and I'll come back. We'll take a 5 minutes break and we'll come back after that. Okay, we'll start again. So, as I mentioned, it is about flow. Reynolds numbers are given, and we are asked to identify which of them are likely to be turbulent. First one is flow in a circular pipe, and its Reynolds number is 50,000. Second one is flow over a sphere at a Reynolds number of 50,000. Third one, flow over a flat plate at a Reynolds number of 50,000. So from this we are able to observe one thing, that the Reynolds number in all cases are 50,000, but in all cases it is not uh, turbulent. Alright, so in the critical Reynolds number for each of these cases is different, so we need to know that properly to identify the right answer. First option, it is option A 1, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So the answer is actually option A 1. For the flow in a circular pipe at a Reynolds number of 50,000, it is turbulent. Whereas the other cases, it is not turbulent. We will see the critical number for flow through these different applications. Critical Reynolds number values for turbulent flows are: flow in a circular pipe, it is 2000. Flow over a sphere, it is 2 lakhs. Flow over a flat plate, it is 5 lakhs. So this is the critical Reynolds number value for obtaining turbulent flows. So when the Reynolds number is exceeding 2000 for flow through a circular pipe, we know that it is a turbulent flows. Whereas when we are concerned about flow over a sphere, we are having a turbulent case value as a Reynolds number of 2 lakhs, and if it is exceeding 2 lakhs we can call it as turbulent flows, but in our case it was 50,000 for flow over a sphere, so it was not turbulent flow. And third one, flow over a flat plate, again the critical Reynolds number value is given as 5 lakh, whereas in the question it is given as 50,000. So answer is only one. First one alone is the turbulent case, rest of them are not turbulent case according to the Reynolds number given in the problem, because it is less than the values, critical values. So the critical Reynolds number values for turbulent flows in a circular pipe is 2000. In a flow over a sphere is 2 lakh. Flow over a flat plate, it is 5 lakh. So keep these things in mind. So it is required you memorize these values so that it will come handy in the later cases. So that is for question 9. Now we will go to question 10. So in question 10 it is given that which of these are characteristic features of turbulent flows. And first one, it is always three-dimensional and always fluctuating. Second one, low diffusivity. And third one, do not obey Navier-Stokes equations. So when we are talking about turbulent flows, what are all the characteristic features of turbulent flows? In the first few case slides itself, we have seen it is about chaotic motion. We have high diffusivity and high fluctuations. We will be seeing in turbulent flows. But a few more things are given over here. We need to identify them. First one, it is always three-dimensional and always fluctuating. This is true because we are always dealing with the three-dimensional flows and it is always fluctuating. Second one, it is given as low diffusivity. Is it low diffusivity? No. We are able to observe turbulent flows systems have high diffusivity. So second one is false. Third one, do not obey Navier-Stokes equation. Again, this is false because turbulent flow systems obey Navier-Stokes equations. We are not going with the traditional way of solving because it is very difficult to get the solution. Therefore, we are using methods like Reynolds average Navier-Stokes equations to get the turbulent flows solution. So first one is true, second one and third one are false. Option A 1, option B neither 1 nor 2, option C both 1 and 2, option D 2. So okay, answer is actually option A. Option A is the right answer. If it is neither 1 nor 2, it should be 3, right? So answer is option A. 1 is the right answer, and we will see why. First one, always three-dimensional and always fluctuating. Turbulent flows are inherently three-dimensional. Even if time average flow appears two-dimensional, the instantaneous turbulent structures are three-dimensional, unsteady and fluctuating with random and chaotic variations in velocity and pressure over time. These fluctuations are defining features of turbulence. So, turbulent flows are always fluctuating and they are always three-dimensional. Even if time average flow appears 2D, the instantaneous turbulent structures are three-dimensional. So, first one is true. Second one, low diffusivity. When we are talking about turbulent flows, we know it as these systems have high diffusivity and not low diffusivity. Turbulent flows have high effective diffusivity, especially in terms of momentum, heat, and mass transfer. Turbulence enhances mixing, one of the reasons why turbulent flows have much higher transport rates than laminar flows. Turbulent flows have high effective diffusivity, especially in terms of momentum, heat, and mass transfer. These offer higher mixing rates than the turbulent flows because they are having high diffusivity and high fluctuations. Mixing is enhanced in turbulent flow systems. Third one, they do not obey Navier-Stokes equation. Again, this is false interpretation. Turbulent flows absolutely do obey the Navier-Stokes equation. The equation remains valid. It is just that solving them directly for turbulent flows is extremely challenging. Hence, we go for DNS, that is direct numerical simulation, and RANS, that is Reynolds average Navier-Stokes equation, etc. Turbulence modeling is required because not because the equations fail, but because they become computationally intractable at higher Reynolds number. I hope it is clear. Turbulent flows are inherently three-dimensional problems. We are solving for the unsteady and fluctuating systems with random and chaotic variations in both pressure and velocity over the time. And these fluctuations are defining characteristics of turbulence flows. And turbulent flow systems have higher diffusivity, high effective diffusivity, and this help in having turbulent flow systems have higher transport rates than the laminar flows. And lastly, it is they do not obey Navier-Stokes equations. Turbulent flows absolutely obey Navier-Stokes equations. The reason we are not going with turbulence modeling is because it is computationally interactable at higher Reynolds number. Not The reason is not these equations fail at higher Reynolds number. These equations obey and they remain valid at higher Reynolds number. Solving them directly for turbulence flows is extremely challenging, so we go with other turbulence flow modeling like RANS. So answer is option A. 1 is therefore the right answer. So just take a look at it. If you have any doubts, you ask me. Because we have time, just take a look at it. Okay, we'll go to next question now. Question 11 it is. Which of the following statements is true about the turbulence closure problem? Which of the following is true about the turbulence closure problem? First one, it arises only when we do numerical simulation, when we do direct numerical simulation of turbulent flows. Second one, it arises because there are too many equations and too few variables. Okay, and option A 1, option B 2, option C both 1 and 2, option D neither 1 nor 2. So it is about turbulence closure problem, and answer is actually option D, neither 1 nor 2. When we are talking about turbulence closure problem, it does not it arises only when we do direct numerical simulation of turbulence is wrong. In fact, when we do DNS, we don't have the need for closure problems. Second one, it arises because there are too many equations and too few variables. The reverse is true when we have too many variables and too few equations. So we go with turbulence closure and get values for certain variables. So that is where we use the turbulence closure. In general closure relations we use in those cases only, right? when we go with DNS, we do not require the need for, we do not have the need for closure problems. Second, when we have the too many equations and too few variables, that is not the case. We go with the closure problems when we have too many variables and too few equations. So both of the statements are actually false. So answer is therefore D, neither one nor two. We'll have a quick explanation for it. It arises only when we do direct numerical simulation of turbulence. This statement is incorrect. The turbulence closure problem is not specific to direct numerical simulation DNS. In fact, DNS is specifically used to avoid closure problems by directly resolving all scales of turbulence without modeling. The closure problem is primarily associated with Reynolds averaged approaches to turbulence modeling. DNS differs from conventional CFD precisely because it explicitly resolves turbulence rather than requiring Reynolds average Navier-Stokes closure. So, I hope you are getting it. When we use DNS, we use it to avoid closure problems. We directly resolve all scales of turbulence without modeling. So closure problems is directly associated with Reynolds average Navier-Stokes approaches. So DNS therefore it differs from the conventional CFD, where we use the, in conventional CFD we use RANS for turbulence modeling. In DNS, we do not go for the turbulence modeling using RANS. Rather, we explicitly resolve everything happening at all scales of turbulence without external modeling. So, first statement is incorrect. Second statement, it arises because there are too many equations and too few variables. This is also false. This statement actually reverses the actual issue. The turbulence closure problem arises because there are more unknowns than equations, not vice versa. The American Meteorological Society glossary specifically defines it as a difficulty in turbulence theory caused by more unknowns than equations. When Reynolds averaging is applied to the Navier-Stokes equations, the nonlinearity of these equations produce Reynolds stress terms containing velocity fluctuations that require additional modeling. The number of unknowns is larger than the number of equations. This imbalance requires closure assumptions to make the mathematical system tractable. So as I mentioned, uh, it is like a difficulty in turbulence theory caused by unknowns, more unknowns than equations. When we are applying Reynolds averaging, right? When we are applying Reynolds averaging to the Navier-Stokes equations, the nonlinearity of the equations produces a Reynolds stress term in the equations, which contain velocity fluctuations that require additional modeling. So what we are ended up with more variables than the equations. So this imbalance requires us to make some closure relations to get the proper solution. So I hope you are clear now. It arises only when we do direct numerical simulations of turbulence. This is false because we use DNS to escape the closure by directly resolving everything. Second one, turbulence closure arises because there are too many equations and too few variables. The reverse is true, wherein a turbulence closure arises when we have too many variables and too few equations. Because when we do Reynolds averaging of the Navier-Stokes equations, we ended up with Reynolds stress system containing velocity fluctuations. So we are ended up with too many variables, but the number of equations is less. So we require turbulence closure. So these are nothing but some parameters or some values which we apply in the equations, so that the number of equations and the number of variables becomes even. The number of the variables, for the variables we apply specific values. That is what what is meant by closure relations. So that is for this. um, I hope question 11 is clear. We will go to question 12. In question 12, what is given? Which of the following statements is true about Reynolds stresses? First one, they are not stresses per se but stress-like quantities. They are constant across the cross-section of a pipe in a fully developed flow. Option A 1. Option B both 1 and 2. Option C 2. Option D neither 1 nor 2. So answer is actually option B. Okay, A. Yeah, only one is right. Okay, first one is true, second one is false. In the first statement, it is given that Reynolds stresses are not stresses per se, but stress-like quantities. Reynolds stresses are true. They are not stresses, but stress-like quantities. So we call it as Reynolds stresses. So that is true. Second one, they are constant across the cross-section of a pipe in a fully developed flow. Uh, Actually, they are not constant because they are involving fluctuations. We cannot term it as constant across the cross section of a pipe in a fully developed flow. So second one is false. Option A1 is therefore the right answer. We will look at it more clearly in the next slide. They are not stresses per se but stress-like quantities. This is true. Reynolds stresses arise from the averaging process in the Navier-Stokes equations for turbulence flows. They represent the apparent stresses due to turbulent velocity fluctuations, not molecular interactions like true viscous stresses. They act like stresses in the equations, but they are statistical constructs, not actual physical stress tensors from the intermolecular forces. So, Reynolds stresses arise when we do the averaging process in the Navier-Stokes equations for turbulent flows. In turbulent flow systems, we average and we are getting the Reynolds stresses. They represent the apparent stresses due to turbulent velocity fluctuations, not from the molecular interactions, which leads to the true viscous stresses. So we are saying they act like stresses in the equations. They are from the statistical constructs, not the actual physical stress tensors from the intermolecular forces. So option A is true. Second one, it is given that they are constants across the cross section of a pipe in a fully developed flow. So we are saying it as false. In a fully developed turbulent pipe flow, Reynolds stresses vary with the radial positions. So across the cross section, it is not constant. They are varying with radial positions. Near the wall, the turbulent fluctuations are smaller. So Reynolds stresses are low. They reach a maximum at some distance from the wall and decrease towards the center line. They are not constant across the cross section. So second statement is actually false statement. We are not saying, we cannot say it as a constant because near the wall they are small and they reach a maximum at the center at some distance from the wall, and again they decrease towards the center line. So they are not constant across the cross section of a pipe in a fully developed flow also. So second statement is in fact false statement. First statement is true, second statement is false. So have a look at it. We will move to next question shortly. Okay, now we will go to question 13. In question 13, it is asked that which of the following statements is true about eddy viscosity. So we are talking about eddy viscosity and which of the following statements is true. First one, it is a flow property. This is true. Eddy viscosity is about flow property, not about a fluid property. This is true. Second one, it is a fluid property. Again, it is false. Options given are option A 1, option B both 1 and 2, option C 2, option D neither 1 nor 2. So we know that eddy viscosity is a flow property. It is not a fluid property. So answer is option A. It can be both 1 and 2 actually. But yeah, our answer is option A is the right answer. That is 1. We will see why. Eddy viscosity is indeed a flow property rather than a fluid property. Unlike molecular viscosity, which depends on the fluid material itself, eddy viscosity depends on the state of turbulence in the flow. So when we talk about viscosity, right, that is molecular viscosity, fluid viscosity, it is a fluid property. That depends on the fluid material, type of fluid, because water has one viscosity and oil has some other viscosity. It depends on fluid type, fluid viscosity, so it is a fluid property. But when we talk about eddy viscosity, it depends on the state of turbulence in the flow. So it is a flow property and it is not a fluid property. Turbulence eddy viscosity is not a fluid property but depends strongly on the state of turbulence. So turbulence eddy viscosity. Eddy viscosity comes in picture in the turbulent flows. So it is not a fluid property but it is strongly depending on the state of turbulence. So turbulent eddy viscosity may vary significantly from one point in the flow to another and also from flow to flow. So water, if you take, the molecular viscosity is remaining constant throughout the system. In case of laminar flows, we can see. But when we talk about turbulent eddy viscosity, right, uh, it is not a constant thing for a particular fluid. Rather, it is varying inside the fluid itself. It is varying from one point to another and also from flow to flow it is varying. So it is a property of a flow, not a property of a fluid. That is for question 13. So take a minute to analyze. We will move to question 14 shortly. Okay. Now we are going to question 14. In question 14, it is asked that the units of turbulent kinetic energy are dash. Option A, joules per meter cube. Option B, joules per second. Option C, meter square per second square. Option D, joules per meter cube second. So we are asked to find the units of turbulent kinetic energy. So if it is unit of turbulent kinetic energy dissipation rate, it is like variation with respect to time. So that is how we need to calculate for the unit of turbulent kinetic energy dissipation rate. But in this question, we are not asked for that. We are asked for the K. That is unit of K, the unit of turbulent kinetic energy. So answer is actually option C. Meter square per second square is the right answer. Option C is the right answer. We will see the small derivation actually. Turbulent kinetic energy per unit mass is given by K equal to half of U dash square plus V dash square plus W dash square. All those are averaged out, and velocity fluctuations in the xy directions are U dash, V dash and W dash. So kinetic energy per unit mass is given by this, that is K equal to half of U dash square plus V dash square plus W dash square, all averaged out. Because U dash, V dash and W dash are velocity fluctuations in the x, y and z directions. And what is the unit of U dash, V dash and W dash? Their unit is, we all know, it is meter per second because it is velocity values. So unit is also velocity unit only. But now the turbulent kinetic energy is given by half of U dash square plus V dash square plus W dash square. So it is square. Square of velocity value gives us the unit of turbulent kinetic energy per unit mass. Squaring these units of mass, we have meter per second the whole square, and it is meter square per second square. So turbulent kinetic energy is root mean square of velocity fluctuations. So it is given by meter square per second square. So I hope it is clear. Or if you want, right, I can give you the question in a different way. Per unit mass. Okay, now it is more clear, I guess. So that is for question 14. We are now going to question 15. Which of the following statements is true about turbulence modeling? Option A. Mixing length varies from flow to flow but is constant for a given flow. Option B. Barring direct numerical simulation of turbulence, the K epsilon model is the best turbulence model. Option C. The energy equation need not be time averaged in turbulence flows with heat transfer. Option D. None of the above. So, we are given three statements. The actual answer is option D. None of the above is the right answer. I'll quickly give you why everything else is false statements. Uh, so first statement is like mixing length varies from flow to flow but is constant for a given flow. This is false because inside the flow mixing length is not actually constant for a given flow. It is in fact varying as we have seen from the normal distance to the wall. Based on the normal distance from the wall, mixing length is actually varying. So first statement is false. Second one, barring DNS, that is direct numerical simulation of turbulence, K epsilon model is the best turbulence model. Again, this is false. K epsilon is one of the widely known and widely used models, but the different turbulent models are actually there was one more problem with K epsilon question, right? Here K is the turbulent kinetic energy and epsilon is the turbulent kinetic energy dissipation rate. Right, now it is making more sense. So is one of the widely used, but it is not the best model. It actually the choice of turbulence model depends on the application for which we are using, so it is false. Third one, energy equation need not be time averaged in turbulence flows with heat transfer. Again, this is false. If we are using energy equation, we need to time average it as well. The more detailed explanation is given in the next slide. Mixing length varies from flow to flow but is constant for a given flow. This is false. Mixing length varies within a single flow depending on spatial positions, that is distance from the wall in boundary layers, and also flow type it varies, that is jet, wake, different flow mixing length varies. Second statement, barring direct numerical simulation, the K epsilon model is the best turbulence model. This is also false. K epsilon model has limitations in flow with strong adverse pressure gradients, separation or curvature. Other models like SST, K epsilon, K omega or Reynolds stress models, RSM models are better suited for such cases. K epsilon is widely used but not universally the best. As I mentioned, K epsilon is widely used and widely known, but it has certain limitations, like when we are using K epsilon in cases of strong adverse pressure gradient, separation or curvature, it won't work well. Other models like SST, K omega or Reynolds stress models are better suited for more applications in those cases. So we cannot say K epsilon is the best turbulence model. So that is a false statement. And last statement, energy equation need not be time averaged in turbulent flows with heat transfer. Again, this is a false statement. Turbulent heat transfer requires time averaging the energy equation to account for fluctuating temperature and velocity fields. In turbulence modeling, in turbulence applications, what we encounter fluctuating temperature as well as velocity fields. When we are using heat transfer applications, we encounter turbulence in temperature as well. So turbulent thermal diffusivity and Reynolds heat flux are additional terms which will be introduced and we need to model those. So time averaging of turbulent flows with heat transfer is required. We cannot neglect the time averaging in those cases. Energy equation need to be time averaged in turbulent flows with heat transfer. So the statement is also false. So the first statement is false because it varies within the flow. Second statement is false because we cannot say K epsilon model as the best. Third statement, okay, I mentioned false, right? If it is, I mean, yeah, but all three statements are false. If I said as true, I'm sorry, I intended it as false, but yeah. Third one, energy equation need not be time average. Again, it is false. We need to average energy equation also. So that is also false. So our answer is actually none of the above is the right answer. Okay. I hope you are clear. Just read this for a minute. We'll go on next. Okay. I hope it is clear. And that is for today's session actually. In today's session, just a quick recap. So we have seen about turbulent flows and turbulence modeling in today's class. So when characteristic features of turbulent flows is kinetic motion and high diffusivity, high frequency in fluctuations, and also we should be averaging the time interval for time averaging should be larger than the largest eddy, time period of the largest eddy. Mixing wall varies with respect to the normal distance from wall, and when we are solving for turbulence modeling, right, we need to solve additional two equations. One is K equation, turbulent kinetic energy. Other is turbulent kinetic energy dissipation rate, epsilon equation. We need to solve for two additional equations. So apart from a number of equations that we solve in general case, we need to solve two additional equations when we are talking about K epsilon turbulence equations, K epsilon turbulence modeling of the turbulence flow problems. So we need to add those in the number of partial differential equations that need to be solved. Apart from that, you need to count the regular number of equations which we need to solve, which we know now. It depends on if we are having only cold flow systems or if energy transfer is also involved. The problem we have encountered in today's class is only cold flow systems, so we are considering only continuity equation and momentum conservation equation along with the turbulence modeling equation, that is one K equation and one epsilon equation. So and we have calculated Reynolds number, a velocity inlet from the Reynolds number. This is case of wetted perimeter, rectangular duct flow, so we need to calculate hydraulic diameter. And lastly, we have seen some theory about Franz equation, how we can use unsteady state of Franz equation when flow is turbulent, because the flow is turbulent. And again, we can use it for time dependent flow system as well, and we can use it for slow transient flows. We can use it for any fluctuating turbulent flows. We need not restrict it to rapidly fluctuating turbulent flows. And lastly, there is some critical Reynolds number for the flow to be considered as turbulent depending on the system. In a circular pipe flow, it is 2000. In a flow past a sphere, it is 2 lakh. And flow over a flat plate, it is 5 lakh. And lastly, the characteristic feature of turbulent flows is that it is three-dimensional and it is fluctuating, and we are able to see high diffusivity, and these equations obey Navier-Stokes equation. We can give it as a false, right? And lastly, we have seen about turbulence closure problems, and both of the statements were found to be false because it arises DNS we use when we don't have uh, when we can directly resolve it, but when we want to go with turbulence closure, I mean DNS we use when we want to escape the turbulence closure issues. And similarly, when turbulence closure arises when the number of equations is less but the number of variables is high, in those cases only we use the turbulence closure problems. So that is the case. And 12, this is true. Reynolds stresses are stress or not stresses per se but stress like quantities, but they are not constant across the cross section of a pipe in a fully developed flow. This is false. Um, so yeah, eddy viscosity is a flow property, and we have seen unit of turbulent kinetic energy is per unit mass is meter square per second square. And yeah, mixing length varies from flow to flow but is constant for a given flow. It is false. And again, bearing DNS, we cannot say K epsilon is the best turbulence model. We have certain limitations in K epsilon as well. And similarly, we need to time average energy equations when we are dealing with the heat transfer problems. So these are the things. Um, that is for today's class. If you have any doubts, you can ask now, or we will meet again in the next class tomorrow from 6 p.m. to 8 p.m., wherein we can have a summary of all those things we have learned from week 1 to week 12, that is today. And if you have any doubts, you can ask me in tomorrow's class also. We can discuss and we can provide the solution. And that is like a summary session. So even though I am preparing some slides, we can discuss your doubts. So let us, I mean, I'll have one problem from all the classes and will give you an idea of what all the things we have learned. But apart from that, if you have any doubts from the previous classes, you can ask tomorrow. That will be our last class. And yeah, that's it for today's session. So I hope it is clear, so we can close this session actually. Yeah, I will close the session. Time is almost done. So yeah, I'm closing the session. We will meet again tomorrow. That will be our last session. So tomorrow 6 p.m. to 8 p.m. we will see. And if you have any doubts, we can discuss that time. Or yeah, thank you for attending, and we will meet tomorrow. Bye.